Okay, so we're going to start chapter 8 today. There we go. So just a kind of a schedule reminder, today we're doing chapter 8. Monday we're doing chapter 8, and then next Wednesday is our next test. So chapters 7 and 8 only on that test. The study guide is up. So I would highly suggest starting to look at it, especially for the chapter 7 stuff. I feel like chapter 7 is heavier with concepts. So what I mean by that is we didn't have very many reactions to learn in that chapter, but making the decision for the substitution elimination, like kind of weighing all the different what's the word I'm looking for? Conditions, weighing all the different conditions is really kind of the concept side of that. Whereas chapter 8 is actually a good representation of what the majority of our chapters will look like from here until the end of second semester. My cat has decided to jump on my desk. Okay. So the way that chapter 8 will work and the way that we will see a lot of the rest of our chapters work is we're really just going to be looking at a handful of reactions. So chapter 8 has 10 reactions in it. As we go through them, we will talk about the different conditions. So regioselectivity, stereoselectivity. Oh, so someone in the chat said that they can't hear me. Can you guys hear me?
Yeah, I can hear you.
Okay. Oh my gosh, little kitty, just come here. Okay, just sit. You don't need to chew on cords. Just be a good cat. If you know how. Okay. Okay, so we'll talk about regioselectivity, stereoselectivity. With some of the reactions, we'll talk about mechanisms. We don't end up talking about mechanisms with all of them, and some of them, it's because it actually goes beyond this class, so it's not a focus of this class. And then some of them are actually unknown still. So mechanisms are something that people study in grad school, and so it just might be that we don't quite know them yet. So here we go. Our chapter is focused on alkenes, and in this very first super generic introduction slide here, we're looking at the very general version of the reactions we're going to do. So most of the reactions we're going to talk about fall into a category called addition reactions. And so really that means we're adding things to an alkene. Oh my gosh, this cat just rubbing her face on my keyboard. So up here we have our alkene. We're going to add X and Y. So literally we're adding X to one of those vicinal carbons. Yeah, this is definitely the one that's always meowing during lecture. Meow. I like to say she meow yells. Now, today she apparently wants to be cuddly. So in all these reactions, we're going to be adding two things, one to each carbon. Sometimes they'll be the same thing, like a hydrogen to each one, and sometimes they'll be different. What we're adding, or let me rephrase that, how we're adding it is going to depend on what it is. And so what I mean by that is we know that our pi bond is going to be a reactive source. It's a source of electrons. So the pi bond can act as a base or act as a nucleophile. And we've talked about the difference between like a proton transfer and a nucleophilic attack. And really the only difference is whether we're using a hydrogen or something that's not a hydrogen. So this E here is just a generic electrophile. But notice that the steps are the same. We're starting at that pi bond and then bonding to whatever is positively charged. Alkenes are everywhere. So this is a very broad example of where we would find them out in the world and what they're used for. So everything from petroleum to acetic acid, which is vinegar. And we find them in things we eat, like vitamin A. So they are a building block for a lot of larger molecules. Because we have all these reactions that we can do with them, we can turn them into a lot of other things. So they're a really good starting point for a lot of synthesis reactions, which is really just a way to say doing a bunch of reactions in a row. So I mentioned what addition reactions are. We're adding something to that double bond. And we already know what elimination reactions are because we looked at those in chapter 7. And so really, addition and elimination reactions are opposites of each other. And so this does mean that sometimes the reactions are reversible. We can undo an addition with an elimination or vice versa. And one of the ways that we can control that is with temperature. And so we talked a little bit about adding heat to push an elimination reaction. And so that's our kind of our control factor. If we're doing a reaction at high temperatures, then it will favor an elimination reaction. And if we're doing reactions at low temperatures, it favors an addition reaction. And so this goes into enthalpy and entropy. It's not going to be a big focus for us in this chapter, but that is the explanation for it. So for us, we will see heat added to some reactions, or you might even see like just an arrow and then underneath it, it will say low temperatures or an arrow with heat. A lot of times we don't specify the exact temperature because that's going to depend on concentrations and if you're doing it on a really big scale or a really small scale. So we just kind of say, oh, this needs to be cold or this needs to be hot, but without actually saying what the temperatures are. So you might see that on some of the reactions, or we definitely saw it last chapter. And this is why, is that it's helping the reaction go in the direction we want. So reaction number 1. Let's see, actually, no, that's not what I want to do. I want to show you something, but I don't remember if I didn't put it in the slides. Okay, so at the end of the chapter, there is a summary of all of the reactions. It's kind of just looks like a big map. It has an alkene in the center and then arrows going all the way around it, going to all the different reactions. And it has all of the reactions numbered. And I'm bringing this up because I number them so that we can kind of have them organized. It's also a way for me to have them numbered on the study guide so I can tell you which ones you need to know or which mechanisms you need to know. So I'm telling you this because in the slides, I have them numbered that way. So I think in this chapter, we go through them actually in order, but in some chapters, we don't. Yeah, we do go through them in order. In some chapters, we don't actually go through them in order, and it's just because I'm using the numbers at the end. So it's kind of a weird little side note, but I just want to tell you that the numbers that are on here are from that reaction summary at the end of the chapter. Okay. So this is our first reaction. So with each reaction, we're looking at the name, what's happening with it, and any type of details. So regio and stereo details. So reaction number 1 is a hydrohalogenation reaction. The names themselves aren't terribly important, but they do tell you what's happening. So in a hydrohalogenation reaction, that means we're going to add a hydrogen and we're going to add a halogen. So with these, I do like to draw out what I refer to as just a generic reaction. So we always look at very specific examples, But if we want to look at this a little bit more generically, we're starting with an alkene, and we're going to react it with, oh, little kitty cat, where do you want to go? Sorry. We're going to react it with HX. And so X is our generic way to write a halogen. And so when we do this, we also need to define what our halogen can be, because a lot of times we can't use every single halogen. So in this reaction, we can use chlorine, bromine, or iodine. And so let's do that. And then what we're going to make at the end of the reaction is an alkyl halide. So we're starting with an alkene, and then on each of those vicinal carbons, one of them is gaining a hydrogen, and the other one is gaining a halogen. That first example is completely symmetrical. Each of the vicinal carbons has 2 methyl groups attached to it. And so whether we put the hydrogen on the left or the right and the halogen on the left or the right doesn't matter because of symmetry. And so the question that's underneath here, what about regioselectivity? So now this is saying, well, what if it's not symmetrical? So in this example, we have a C, oh, I'm sorry, I don't even know what I hit to do that. We have a CH2 on the right side, so we have a terminal alkene, and then the carbon on the left has 2 other carbons bonded to it. We're reacting it with HCl, and so we're saying, will the chlorine go to the inside carbon and the hydrogen to the outside carbon, or vice versa? And so to answer that question, we actually have to look at the mechanism. So the mechanism and looking at the transition states helps us understand why we follow certain rules. So here is our mechanism for this reaction. First step, proton transfer. So we're starting our arrow at that pi bond, and we're going to the hydrogen of our HX. So in this case, we're using HBr. We know that hydrogen can only bond to one thing at a time. So that second arrow is we're breaking the bond between the hydrogen and the halogen. So this is our transition state. We have a carbocation intermediate, and because of that, this is going to tell us how our reaction is going to take place, what our regioselectivity is. We know carbocation stability. We know that the more carbons a carbocation is bonded to, the more stable it's going to be. So here's our rule up here. The hydrogen's going to bond to the less substituted carbon, which allows the carbocation to form on the more substituted carbon. So the hydrogen will go to the carbon with more hydrogens. The halogen will go to the carbon that is more substituted. This has a name. It's called Markovnikov's rule. And so we actually reference this rule quite a bit. We'll say if a reaction is following Markovnikov's rule or not. And so Markovnikov's rule tells us hydrogens go with hydrogens, halogens go with the more substituted carbon. And so in that second step, we're doing a nucleophilic attack. So we created a bromide ion. We're going from that bromide right onto that carbocation. The last bullet point then is asking about stereochemistry. If we've created a carbocation, what is the geometry of that carbocation?
Trigonal planar.
It is trigonal planar. So when that bromine bonds, when we do that nucleophilic attack, it can bond to the front side or the backside. And so our stereochemistry here is that we're going to make a racemic mixture. We're going to have an equal amount of R and S, or the bromine will be in equal amounts of dash and wedge, however you want to think about it. But because it's a trigonal planar structure, geometry, the bromine can attack from either side equally. So it will be a racemic mixture. So this gives us our reaction, it gives us our mechanism, our regioselectivity, and our stereochemistry. Because we have that carbocation, we do have to make sure we're thinking of or looking out for carbocation shifts or rearrangements. So anytime we have those, and we'll actually look at those in a couple slides, but anytime we have that carbocation intermediate, it's one of the annoying things, to be honest, but one of the things we have to keep an eye out for and look for. Any questions on our first reaction? Okay, then let's look at number 2. Oh, I'm sorry. Let's look at carbocation rearrangements. Oh, I switched the slide orders. That's why. Okay. So this is looking at those carbocation rearrangements that I mentioned. So here is our first step of our mechanism. We're doing the proton transfer. We create our carbocation. So our hydrogen went to that end carbon and it created a secondary carbocation. But we're going to do a hydride shift. So we're going from the electrons of that carbon-hydrogen bond over to the carbocation. And so now our carbocation has moved over one position and it's now tertiary. So now our halogen can do a nucleophilic attack. And we can add that chlorine to that carbocation. Now here's honestly something that's kind of just annoying about this is anytime we can do a hydride or a methyl shift, we're going to get a mixture of products. So this is the same reaction down here. This one is without doing the rearrangement. So this is starting with that secondary carbocation, and then the other one is with the rearrangement. So we will always get a mixture of products. The major product will always be after that shift has occurred. So whether it's a hydride shift or a methyl shift, that's going to be the more stable carbocation. So that will always be our major product. However, because the other carbocation forms first, it will actually be faster to react with that one. So we will still get the product without that rearrangement, without that shift, as a minor product. And look at those percentages, 40 and 60. That's not great because that means that that's a pretty big mixture. Of course, we'd want it to be something like 95 and 5 because it would be easier to produce. But in reality, this is what happens. It's a mixture of, or it's a battle between which one's more stable versus which one reacts faster. And the stable one is always going to win. It's always going to be the bigger percentage, but not by a whole lot. So we always have to look for carbocation rearrangements, and the carbocation with the shift will always be our major product. Did you say that the placement of the arrow on the nucleophile attack? I probably did. So the question says, did you say that the placement of the arrow of the nucleophile attack on the carbocation matters? So we have to start at the lone pair of our nucleophile, and we want to end on that carbon. So for the other one, let's see, we'll go right here. When we have the secondary, we would start at our chlorine and end at that carbon. So I do say you start at the lone pair. Technically, we don't have to draw those lone pairs in. So you can just start at the side of your nucleophile. And yes, there's another question. The rearrangement product will always be the major product. You're welcome. Any other questions on this first one? Okay. Then let's look at reaction number 2. Oh, I'm sorry. I have a practice one. I should probably actually look at my own notes every once in a while. Let's do a practice one. Oh. No, let's do this, and then we'll go back to the practice one. Sorry, my slides are not in the order I expected them to be in. This is what happens when I prep during Christmas break and then don't go back and look at them again. Okay. Reaction number 2. This is also a hydrohalogenation reaction. So we're still adding a hydrogen and a halogen to our 2 vicinal carbons. Specifically, this reaction is an Anti-Markovnikov Hydrobromination. So we're adding a hydrogen, we're adding a bromine, but we're going to add them anti-Markovnikov. So that means the hydrogen is going to go to the more substituted carbon. That circle was a little out of control. And the bromine will go to the less substituted carbon. So this is the opposite of what we just saw. That's what makes it anti-Markovnikov. So we know that we're going to start with an alkene. We're going to react it with HBr. So we don't have any other options on this one. We don't have any other halogens we can use. This is just a bromination reaction. And we're going to react it with ROOR. The way that we write out a reaction most of the time is whatever is over here on the left is usually our organic starting material. So, the carbon-based thing we're talking about. And then whatever is above and below the arrow are the extra reagents we need to use. And so sometimes that might include catalysts. In this case, it includes this ROOR, which is a peroxide. So the R's are there because it's some kind of carbon. And it really doesn't matter a whole lot what it is. We're not going to talk about the mechanism for this one. We will actually look at the mechanism for this one when we get to chapter 10. It's a different style than the patterns we look at in this chapter. So we group it with the style it fits with. So we'll look at it later. So this could be methyls, ethyls, propyls. Not a big deal. We do know that that's hydrogen peroxide, so H2O2. You probably have some in your bathroom, in your kitchen somewhere. That oxygen-oxygen single bond is what makes it a peroxide. And that bond is really weak. So we utilize that in this reaction. So alkene plus HBr and peroxide will make an alkyl bromide. We know the regiochemistry. It's going to be anti-Markovnikov. It will also be racemic. So if we're creating a stereocenter, it will be a racemic mixture of the R and the S of those 2 isomers. Okay, let's do a practice problem with these first 2. So I'm going to go back up a slide to my blank one here.
I have a question.
Yeah, go right ahead.
For this reaction, is it always just going to be hydrogen and bromine?
Yep.
Okay.
Actually, I'm going to move that up. Sorry, I don't know why I started right in the middle. Okay. We are going to draw the products for these 2 reactions. For this one, we're going to look at the major and the minor. For the other one, there's only one. So we have an alkene. When we have an alkene and we're going to react it with HCl on one side, we're going to react it with HBr and ROOR, so a peroxide on the other side. With both of these reactions, we know we're adding a hydrogen to one carbon and we're adding our halogen to the other carbon. So a big part of this is knowing which side gets which. So we have two carbons here. We have, let's see, let me just number them. Call it carbon 1 and carbon 2. So I'm just going to go left to right. So we'll start over here with the HBr and the peroxide. Which carbon is my bromine going to add to?
Is it the right side? The less substituted side?
One.
One, yeah.
Yeah, it is going to be 1. It is the less substituted side. Yeah. So we're going to draw out just our regular carbon structure. So none of the carbons are changing at all. What's kind of funny about organic chemistry is that it's a carbon-based field of chemistry, but most of our reactions don't change the carbon structure. We're adding other things to it. So a lot of times you can start by just drawing out the carbons. And then you guys are right. So we're going to add our bromine to the less substituted side. And I'm going to draw my hydrogen in just so we know where it ended up. Definitely not required though. We know we don't have to draw in those hydrogens. And that double bond does go away because we're using those electrons to form those new bonds. Oh no. My laptop just told me it wants to restart. Remind me tomorrow. Okay. So on the other one then, we know that this one was an anti-Markovnikov rule. We know that the other one is going to follow Markovnikov. So I'm going to actually start by drawing out our carbocation. So when the hydrogen first adds to carbon number 1, we'll get a carbocation on carbon number 2. So that's going to be one of my products, adding the chlorine right there. And I'm going to put my hydrogen there as well. Will this one go through a carbocation rearrangement?
Yes.
Yeah, so we have a hydrogen right here that can shift over, and we will end up with a carbocation in the middle. So we go from secondary to tertiary. So our other product and I'm still going to put my hydrogen, that original hydrogen on the end there, will look like that. So our chlorine will add to carbon number 2 and carbon number 3 because of that carbocation rearrangement. So which one's going to be our major product, the green one or the blue one?
Blue.
Good. Questions about any of those?
So is the reason you did that rearrangement is because you don't want chlorine and hydrogen facing the same way?
No, it doesn't have to do with that. It's because of the carbocation stability. So in the green structure, we had a secondary carbocation. And so anytime we have a carbocation, we want to look at the neighbors to see if we can make it more stable. So if we would have done a shift to the carbon on the end, to carbon number 1, it would have become primary. So that's not going to happen because that makes it worse. But if we shift it to the carbon on the inside, it makes it tertiary. So the reason we do it is to make the carbocation more stable.
Okay, thank you.
Yes. So question in the chat says, can you show the mechanism using HCl? I'm confused at exactly what's shifting. Yes. So I'm going to do a little erasing just so I can have some space for it. See, I'm going to erase the original structure too. We'll just start that over. Okay, so here's how our mechanism goes. We're going to start from the bond onto that hydrogen. We break the bond between the hydrogen and the HCl. So this is our first step. So our proton transfer. And that's where we're at. So we have a hydrogen on that end carbon. We create a carbocation. Now at this point, our chlorine can react with that carbocation and we would make the green product, our minor product down here. But let's look at the shift. On this middle carbon, there is a hydrogen. And so when we draw in our 1,2 hydride shifts, we do need to show that hydrogen. It's one of the few times we need to show our actual hydrogens. And so to do the shift, we're going to start at the bond of that hydrogen and go right to that carbocation. So that's showing us that the hydrogen is moving over and taking its electrons with it. So this is my 1,2 hydride shift. And so I have that hydrogen that just shifted over is right there. And now I have a carbocation on that center carbon. And so then the last step of the mechanism, I have my chloride ion that we created all the way over here. That chloride ion shows back up. We're going to go from that chlorine right onto that carbon. And so then what we end up with, right there. You're welcome. And so what's nice about these two reactions is that we can utilize them to add a halogen. If we want it on the left or we want it on the right, we can pick which reaction we want to do to get the results we want. So a lot of times we'll see that in chapters where it's kind of the same thing. We're adding the same groups or elements, but in different ways. And so sometimes it will seem redundant, but it's really so that we can have options in how we add things, not just what we're adding. All right, questions about these couple before we look at the next reaction? Okay, good question so far. So this takes us to reaction number 3. And reaction number 3 has a couple parts to it. And within this section, we're looking at hydration reactions. So hydration is really just a fancy way to say that we're adding water. And so usually that means that one of the carbons will get a hydrogen, one of the carbons will get an OH. So we're using the pieces of water. We're going to look at 3 ways to do this, 3 ways to add water. 2 of them are going to follow Markovnikov's rule. One of them is going to be an anti-Markovnikov's rule. And so even though we have 2 of them that are both Markovnikov, there's a difference between them. And so we'll talk about that as we look at them. So our first one that falls into this grouping, number 3A, it is an acid catalyzed hydration. So hydration, we're adding water. Acid catalyzed, that means there's an acid hanging out in there. So here's our reaction. We're starting with our alkene. We're reacting it with water. We're reacting it with an acid catalyst. So notice it's in brackets. So if you remember back from general chemistry, brackets mean concentration. And so sometimes you'll see it written this way on the arrow, and it's kind of a way to say that we don't need it in a 1-to-1 molar ratio. We just need a small amount of it. So another way that you might see it written out is that it will say that we need a catalytic amount of it, which is just honestly, it's a really generic way to say we need a small amount of it. Right here, it's written as sulfuric acid, but you might also just see it written as H+. You might even just see the word acid written there. Depending on what the reaction is, sometimes the specific acid matters, and sometimes we just need an acid. So you'll see it written in different ways. If this was a test question and you wrote H2O and H+, that would be completely okay. If you wrote H3O+, that would be completely okay and completely accurate. So those are all saying the same thing. They're all saying that there's water with some acid present. What we're going to make is an alcohol. And this is following Markovnikov's rule. So our hydrogen went to the less substituted carbon, and our OH group, our alcohol group, went to the more substituted carbon. This is forming a carbocation intermediate. We're going to look at the mechanism on the next slide, but because it's forming that carbocation intermediate, we do have to keep an eye out for potential rearrangements. Because it's a carbocation intermediate, it will be racemic. So that's one of those nice trends, is that we can kind of group things together. When we have carbocation intermediates, that will create racemic mixtures because our nucleophile can add to either side. So we know what we're starting with, we know what we're making, we know the regiochemistry, we know the stereochemistry. Let's look at the mechanism for this one. Now, because of the way our chapters are divided, the mechanisms will look very similar. Hey, shh. She's just standing in the hallway yelling at me. Okay, so the mechanisms are all going to look super similar to each other because they're all alkenes reacting, and they get grouped together based off of how they react. So this is the mechanism for reaction number 3A. We're starting with a proton transfer, which is the same thing we started with in our last reaction. So notice the way it's written here. We're starting with H3O+. So we're starting with that water in acidic conditions. So we're going from the pi bond onto that hydrogen. So our pi bond is bonding to that hydrogen. Notice our hydrogen gets added to that less substituted side. And the carbocation is going to form on that more substituted side. So in the second step, nucleophilic attack. Right here in the middle, I'm going to put look for carbocation rearrangements. So in this example, we won't need to do one because our carbocation is tertiary. And if it were to shift to the other position, it would either become primary if it went to the left or secondary if it went to the right. But either way, it's not becoming more stable. So we don't need to do a rearrangement here, but we do have to keep our eye out for them. So in that second step, we're doing a nucleophilic attack. So we're going from that oxygen right onto that carbocation. One of the things we talked about in chapter 7 is that when we have a neutral nucleophile, after it attacks, we have to remove the extra hydrogen. So that's exactly what's happening here as well. Because our water was neutral, right here we have neutral water, we have to do one more proton transfer to get rid of the extra hydrogen on that oxygen. So we're using another water molecule, grabbing onto that hydrogen, breaking that bond between the hydrogen and the oxygen, and we make our alcohol. Now, the water then becomes H3O+ again. And remember, one of our definitions of a catalyst is that it's not used up in a reaction. So the catalyst should be reforming at the end of a reaction. So we started with H3O+ and we remake the H3O+ at the end of that reaction. So it is a way for us to show that the acid is a catalyst because we are reforming the catalyst by the end of the reaction. I always think that that's kind of a good thing to look for when we're talking about what the catalyst is, because it kind of provides proof that it's acting as a catalyst, or it's following all the definitions of a catalyst. Questions at all about our mechanism here? Okay. So one more example of this, and it's really combining some chapter 7 stuff into chapter 8 here, but we have our alkene and we have our water, and if we're using dilute acid or a catalytic amount of acid, we're going to go through the addition reaction. But if we have our alcohol and we're using concentrated acid, then it's going to go through the elimination reaction. And this was one of the last reactions we looked at in chapter 7. So this is really just a way to say that this reaction is reversible. And if we want it to go in the addition reaction direction, we want it to make the alcohol, then we would want to use excess water. This is Le Chatelier's principle at work here. So remember way back when you learned about Le Chatelier's principle, it says that if you add in more reactant, it will push the equilibrium towards the product. So we're adding in excess water to push the reaction towards that alcohol. That's why we use a dilute amount of acid. So kind of a little side thing there, but it is a way to connect those two chapters together. All right, we have 3 ways to add on this alcohol. We've talked about one of them so far. So here's reaction number 3B. The name of this reaction is a little weird. Oxymercuration demercuration. So there's going to be some mercury involved. This reaction also follows Markovnikov's rule. So reaction 3A and 3B both are following Markovnikov's rule. The hydrogen is adding to the less substituted carbon. The alcohol is adding to the more substituted carbon. The difference between them, though, there's no carbocation in the mechanism for this reaction, which means there's no carbocation rearrangements. So here's our reaction. We're starting with our alkene, and we are reacting it with mercuric acetate. So right here, HGOAC2. So an AC is an acetyl group. When it has the oxygen attached to it, it's an acetate group. So it looks like this guy right over here. So we would have a mercury right here and then one more of those attached to it. So this is mercuric acetate, water, and then NaBH4 is sodium borohydride. The mercury is a catalyst. It is a Lewis acid catalyst. And so we'll see Lewis acid catalysts pop up every now and then, probably like one a chapter. But they're going to help our reactions because it is a metal-based reaction. It's falling more into the inorganic side of things. And so we're going to look at part of the mechanism on the next slide, but we don't actually look at the mercury part of the mechanism. What we're forming, though, is our alcohol. And in this reaction, we are going to follow Markovnikov's rule without any of those rearrangements. So we're using a very specific alkene here. And the reason why is because if we were to do this reaction with just our acid and our water, we would get a mixture where our alcohol would add here, but it would also go through a methyl shift and our alcohol would add here. When we do this with the mercury reagents, it's not going to go through that shift, and we're only going to get the one product without that carbocation rearrangement. So again, it's giving us very specific options on where our alcohol can add. So let's look at part of this mechanism. It goes through this mercury addition, and because the mercury is adding to that alkene, it's creating this right here. So it's creating this mercury carbon-carbon ring, and our nucleophile will then add to one of those sides. But because we never technically form a carbocation, it doesn't allow for a carbocation rearrangement to occur. Do I have one more slide? No, I don't. The second half of the reagents, the sodium borohydride, breaks off this mercury and replaces it with a hydrogen. So actually, let me talk about that for a second, because I don't think we've come across this yet. But notice that it's numbered 1 and 2. So what that means is that we wouldn't just add everything all together. We would react the alkene with mercuric acetate in water. They'd react for however much time we would need to. And then in a second step later on, we would add in the sodium borohydride. So it's really just saying you don't add all these ingredients together all at once. They have to be added in at separate times. So sometimes we need those numbers to signify that they're added in at different times. For the reaction we just talked about, if we wrote it as water and acid, we wouldn't want to put in numbers, because those two ingredients do get added in at the same time. So be really careful as you're learning these reactions, as you're memorizing reagents, that you are paying attention to whether or not they have the numbers or not, because it does actually make a difference as to how we write it out and what we would make. So something to care about, not just ignore. All right, we have one more in this category. Reaction number 4. So this is our last hydration reaction. And this is a hydroboration oxidation reaction. So we're using boron to do an oxidation reaction. Starting with our alkene, we are reacting it with, again, another 2-step reaction. Let's see, I think I'm just going to define some things. I'll start right here. BH3, so a boron with 3 hydrogens attached, is borane. THF is a very common solvent. It's tetrahydrofuran. Looks like that. Oh, let me give you a little side note. Okay, since this is our first kind of full reaction chapter, let me go right here. All right, I want to bring this up just because I'm saying these things and I realize you guys don't know if they're important or not. I'm telling you names like mercuric acetate, sodium borohydride. You honestly don't need to know those names. I'm telling you them so that hopefully they'll make them stick in your head better. As you're reading the chapter, you know what they're talking about. If you're watching other videos, you know what they're talking about. We don't write the names out though. When we're writing the reactions, we are writing the chemical formulas. You're going to write NaBH4, not sodium borohydride. I'm giving you the names so you have full information, but it's not something that you need to have stick in your head. With this one, same thing. BH3 is borane, THF, tetrahydrofuran. You don't necessarily need to know either one of those. THF is going to come up in multiple reactions throughout our semester. So it might be one that you would want to add to a list. If you're creating that little acronym list, that would be a good one. How would we be tested? So with all of these, how you're going to be tested on them is like this. I'll give you the reaction. I'll give you the, well, okay, there's three parts. There's starting material, there's reagent, and there's product. You're going to be missing one of those. So in the way that we did our practice problem, I gave you the starting material and I gave you the reagent. We were filling in the missing product. If I gave you the starting material and the product, you should be able to fill in the missing reagent. So you're going to fill in, I always call these box problems because on the test you'll see boxes where you're drawing your structures in, but you're going to be filling in the missing piece in those boxes. With the ones where we've talked about the mechanism, you might be asked to draw out the mechanism as well. On the study guide, I tell you exactly which mechanisms you need to know though. So for this chapter, I think there's only 3 of them that you need to know fully, but it is on the mechanism, or I'm sorry, it's on the study guide. Okay, so we have BH3, we have THF in our first step. In the second step, we have hydroxide, peroxide, and water. And we make an alcohol. Now this is an anti-Markovnikov reaction. So our hydrogen is going to go to our more substituted carbon, and our OH is going to go to our less substituted carbon. Stereochemistry for this is a stereospecific reaction. So that means that the stereochemistry of our product depends on the stereochemistry of our reactant. New word right after that, or new phrase. It's a Syn addition. So we actually have talked about anti-reactions. We had one anti-reaction in our last chapter. This is a Syn addition. So if we look at the example on the bottom here, we like to use rings for this because it helps us see stereochemistry a little bit easier. But we have our alkene, we have our set of reagents, the hydrogen and the OH. Notice that they have the same stereochemistry. They're either both wedges or they're both dashes. So syn means same. And so it's telling us that the hydrogen and the OH are going to add from the same side of the molecule. So in both of these examples, the hydrogen is on the more substituted carbon and the alcohol is on the less substituted carbon. But on one of them, they've both added from the top of the molecule, and on the other one, they've both added from the bottom of the molecule. So we will get a mixture of the two, but they will have the same stereochemistry. So Syn addition, they're going to add to the same side. So that's what the syn means. I'm sure there's some Latin prefix thing going on there that I just don't know off the top of my head. But yeah, that is our Syn addition for that. Okay, we're going to look at the mechanism for this one. It's a little crazy. You do not need to know it for the test, so we're not going to look at it in full detail, but I want you to see parts of it. So we're reacting this with BH3 in that first step. And so the boron kind of splits apart, and we add a BH2 to one of the carbons and a hydrogen to the more substituted carbon. This actually happens 3 times in a row. So down here, I have it written as R3b. So there's a boron. That boron is going to be bonded to 3 of our alkenes at the same time. In that second step, we added in hydroxide, peroxide, and water. This is where those come in. So the hydroxide is going to bond to the boron. We do this weird shift here so that carbon group, what was this carbon group right here, that was our alkene. It shifts over and bonds to that oxygen. And so eventually it's able to break apart and we get our alcohol with our alcohol attached to that less substituted carbon. So this is a really intense mechanism because it goes through so many different steps. It's not one that will be on the test, but it does help to show why that oxygen is on our less substituted carbon, and it has to do with the way that boron is bonding to it. So you won't see this one on the test. Don't memorize it. It will be a waste of your time, but there's a little bit of it. All right, we're gonna practice one. So we're starting with the same alkene. We're going to react it with 3 different sets of reagents. Oh, made that last spot real small. Let's try that again. We're filling in some products. Numbering some carbons just so we can talk about them. So these are the 3 reactions we just talked about. We know that they are all hydration reactions. And so because they are all hydration reactions, we know that 1 carbon will get a hydrogen and 1 carbon will get an alcohol. So it's just a matter of regiochemistry. Where do they go? So let's start with the one we just looked at. Let's go from right to left. Let's start with the boron one. I'm going to draw my carbon structure because our carbon structure is not changing. Where is my alcohol going to go in this reaction? Which carbon?
Would it be to the less substituted?
Yeah, the less substituted. So carbon number 1. And I'm going to put my hydrogen in there just so we can see where it went. But this is an anti-Markovnikov reaction. So our alcohol is going to go to that less substituted carbon. So in this case, carbon number 1. What about the next one over? So the mercury-based one. We have mercuric acetate, some water, sodium borohydride. Let me draw my carbon structure. Where's my alcohol going to add in this one?
In the more substituted?
Exactly. So we're just kind of switching their location. So this one's a Markovnikov reaction. And then in our first one on the left there, we have some water and acid. Let me draw out our carbon structure. Where's our alcohol going to add on this one?
Would it also be in the more substituted?
It is. Now this one actually has 2 products. So what else do I need to do to look at my second product for this one?
Would it be the carbocation intermediate?
Yeah, so if we think about what the carbocation will look like for this one, it's going to be right there. So I'm going to do a hydride shift. So my alcohol will also add to carbon number 3, to that center carbon. And my hydrogen's still on the end over there. It hasn't moved. So which one of those would be my major product, the top one or the bottom one?
The bottom one?
Good. So if this was kind of the reverse type of question on the test, if you were given this, you might have to fill in the missing reagents. And because we know it's anti-Markovnikov, we would know that we would use the boron-based reagents to get that alcohol to that end carbon. Any questions about that?
Could you flip the OH and the hydrogen to the other side for 4 or 5?
Well, so technically, because of the way this one's drawn, we could, but remember what we're always adding them to the alkene carbons. So because this one's symmetrical, if we would have drawn it with our alcohol over here, it's the exact same thing. But if this was like a propyl group on that end instead, then we wouldn't be able to do that.
Okay, got it.
Okay. Let's see. Let me check our time. Okay, we're good still. All right, reaction number 5. So reaction number 5 is a hydrogenation reaction, which really just means we're adding hydrogens. So we're starting with our alkene. We're adding hydrogen. And we're using a catalyst. So we're using some type of metal catalyst. This is platinum. PT is platinum. You will also see palladium, PD. You might see something else, but really, if you see a metal underneath the arrow, it's a catalyst. We don't use it, or I'm sorry, that's not the right way to say that. It doesn't show up in the product. So you might see different things under the arrow, different types of metals, but platinum and palladium are definitely the most common. Our alkene becomes an alkane. So each of those carbons bonds to the hydrogen. So we don't have to talk about regiochemistry here, because whether the hydrogen goes here or here or here or here doesn't matter. They're both hydrogens. So we don't need to talk about which hydrogen goes to which location, because it doesn't mean anything. We do need to talk about stereochemistry, though. It's a Syn addition. So that means both hydrogens are either going to add from the bottom or they're both going to add from the top, but it means that they're both adding from the same direction. So this one does involve a metal catalyst, so just kind of like that mercury one we were looking at. And so we don't talk a lot about the mechanism behind this one. We are going to talk a little bit about why it's a Syn addition, though. This is actually a mechanism that's not fully understood yet. It's not one that's been completely worked out. But one thing that we know about it is that the alkene, so all of this down here, this dark gray, that's our metal catalyst. So the hydrogens are bonding to that metal. And so when the alkene approaches it, the hydrogens are going to approach from the same side. So that's why we get the Syn addition. So you don't need to know the mechanism. Really, nobody fully knows the mechanism yet. But this is just kind of to help you see why we get a Syn addition, and it might help you remember that a little bit easier too, if you kind of picture the alkene approaching the metals and the hydrogens. I do have a practice one for this, though. Okay, so we're going to look at this alkene. So we have a cyclohexene with a methyl on one of the carbons and ethyl on the other. So really it's just a way for them not to be the same. And we're going to add hydrogens to it. So if we were to draw this product out, we know that we're going to add a hydrogen to each of those vicinal carbons, each of the double bonded carbons. But we want to show stereochemistry in our answer because we are going to create 2 chiral centers. So we're going to draw our product with the stereochemistry. We want to make sure that we're using dashes and wedges. Oops. To show a full answer. And so how we would do that in this, because our hydrogens are either both going to add to the top or both going to add to the bottom, that means that our methyl and our ethyl will have the same stereochemistry as well. So they will either both be wedges or both be dashes, because the hydrogens that we add on are either both going to be dashes or both going to be wedges. So because the hydrogens are adding from the same side, it's going to force the other substituents to be on the same side either. So they will either both be dashes or both be wedges, and we will get a racemic mixture of these two. So we'll get an equal mixture of each of those isomers. Questions about that at all? Okay. Number 6. Number 6 is a halogenation reaction. So we've done hydrohalogenation, where we did a hydrogen and a halogen, but this one is just halogens. So we're starting with our alkene. We're going to react it with a halogen. So I'm going to put X2 here, our halogen, and our halogen can be chlorine or bromine. And that's pretty common. Iodine is often not reactive enough because it's so large, and fluorine is often so reactive that it can actually be explosive. So we often won't see either one of those. We won't see either extreme, and we stick with just the chlorine and the bromine. There's exceptions to that, of course, but that's why we often will just see chlorine and bromine used. Our solvent that's underneath the arrow there, so CH2Cl2 is methylene chloride. So literally just a carbon with 2 chlorines and and 2 hydrogens attached to it. Very, very common solvent. We even use it in lab just to clean things because it will dissolve just about anything. So very common to see this used. And what we're going to make is a vicinal dibromide, or let's make that a little bit more generic, vicinal dihalide. So vicinal means that they are on next door neighbors. Let's do a little vocab here. If we had 2 halogens on the same carbon, the word that we would use for that is that they are geminal, so meaning they're on the same carbon. And then if we have halogens on next door neighbors, they are vicinal. And this isn't just for halogens. This is really just a location thing. So we could use that to describe alcohols, ketones, ethers, anything. It's just a way to describe location. So vicinal just means that they're on next door neighbors. Dihalide tells us that it's 2 halogens that are on next door neighbors. We don't need to talk about regiochemistry because we're adding 2 of the same thing. So if we're adding 2 bromines or 2 chlorines, it doesn't matter which chlorine goes to which carbon. Stereochemistry, this one's an anti-addition. So we've had a couple that are syn additions. This one's an anti-addition. So the example on the bottom is showing us what that means. So we have our alkene, we have our cyclopentene, excuse me, and we're reacting it with Br2. An anti-addition means that one of the halogens will add from the bottom and the other halogen will add from the top. So they're adding in opposite directions. So the way that we show that, we have bromine on a wedge, bromine on a dash. So that shows us that one's on top, one's on the bottom, and then the opposite. So having the opposite locations with the opposite stereochemistry. So the dashes and the wedges just switch with each other. And so that's the way that we can show that it is an anti-addition. If the halogen was Cl2 in the example, would we still? Yes. So if we were using Cl2 instead of Br2, we would still use methylene chloride. So methylene chloride is essentially just like the liquid that they're being mixed together in. It's the solvent for this. So it's not participating in the reaction at all. So a good question, but we would definitely still use the same solvent. Do I think I have a blank slide? Oh, we're going to look at mechanism first, and then we'll do a practice one. So mechanism for this one, we're going to see a mechanism similar to this one for a couple other reactions. So it looks a little bit different now, but we'll have a couple others that will fit into this same pattern as we start to look. So reaction number 6, mechanism. Here's where we start. We are doing a couple things happening here. So it's kind of a little bit of a domino effect. So I'm going to start by talking about it with this arrow. We're going from the pi bond onto that bromine. That's a nucleophilic attack. Now, in order to do that, that means that that bromine had to be a little bit positive. Remember way back when you learned about London forces. And when we learn about London forces, what we learn is that there's an electron cloud around our molecules, and when they are nonpolar, so in this case, we have a bromine-bromine bond, it's being shared equally, it's a nonpolar bond, but what happens is that as those electrons move, just naturally moving around, the electrons might end up on one side of the molecule, making it partially negative and making the other side partially positive. This is an instantaneous temporary dipole, and it's just caused from the electrons moving around. And as soon as those electrons move around again, it might shift to the other bromine, or it might go back to being uncharged. So it's completely changing all the time. But this is how we get London forces, those attractions. It's an attraction between the instantaneous temporary dipoles of those nonpolar molecules. So that's where that first reaction step happens. The pi bond is attracted to the bromine when it temporarily has a positive charge, partial positive charge. At that same time, the other bromine is going to break off. So this is the loss of a leaving group happening. Now, that third arrow, when the other two arrows happen, this carbon is going to end up with a partial positive charge because the alkene bond has broken. The bromine is an electronegative atom, and it has lone pairs. So we're doing one more nucleophilic attack over here because of the attraction between that carbocation with a partial positive charge and that bromine with all of its electrons. So we have a lot going on just in that first step, but it's because of the movement of all of those electrons. Second step, we've created a bromide ion. So this is what was our leaving group. This is the leaving group that broke off. We're going to do a nucleophilic attack. Oh, this is the name of that intermediate. It's a cyclic bromonium ion. You do not need to know the name of that, but in case you see it, don't know what it means, it's just referring to that little triangle, that carbon-carbon bromine intermediate. So the bromine's going to bond to one of those carbons. That 3-atom ring, that triangle, is super unstable. It has horrible bond angles, so it's going to react really fast. The bromine bonds, and then this bond breaks. So this is technically the loss of a leaving group. Because that carbon-bromine bond is breaking, the bromine is our leaving group. Now, it's not leaving very far because it's still bonded to the other side of the molecule, but here's what we end up with. We have our 2 carbons that were part of that double bond, and then each one of them is bonded to a bromine. So through this reaction, we had to bond to each bromine and break the bromines apart. And so there's a lot of movement of electrons that has to happen to make that occur. So kind of a weird mechanism, but like I said, we will see this similar type of pattern show up in a couple other ones that we'll look at. And this also, let me get a different color here. This step right here is showing us why it's an anti-addition. The one bromine that's in the triangle is on top of that molecule, and the other bromine is adding from the bottom. And so we have an addition from each side. That's where we get that anti-addition from. Lost my spot in my notes. There we go. So this is also showing the anti-addition, just a couple more examples of it. It does fall into that stereospecific category, which just means that the stereochemistry of the products depends on the stereochemistry of the reactants. So if we start with an alkene that is either cis or trans, it's going to affect what our product will be because our bromines are adding anti. So if we're starting with a cis alkene, here's our bromines. Notice we have a dash and a wedge, a dash and a wedge. We've just switched where the dash is and where the wedge is. And then when we start with a trans alkene, again, we're going to add a dash and a wedge. There's only one product for this one, though, because it's a meso compound. So going back a couple chapters there with that word, but remember that means that it's the exact same as its mirror image. So this one over here is the exact same thing. It's just we've rotated around this bond just so we can see it in a different way. It makes it a little bit easier to see that if we had the other version where we had just dashes, those are the exact same thing. So it is the same as its mirror image, and that's what makes it meso. So really, long story short, story behind this slide is you do have to pay attention to the stereochemistry you're starting with, how you're adding in those halogens so that you get the correct stereochemistry for your product. The easiest way to do that, though, is to draw it in the same way. So keep that shape, and then add in your halogens, 1 dash, 1 wedge. And that will make sure that you are drawing it correctly. And I think I have a blank slide. Good. I think this will be our last thing we're looking at then. Oh, one more thing as I'm writing this out. So we talked about the methylene chloride, that CH2Cl2. Someone even asked a question about it. If you see this written without that, it's still the same reaction. I know that's not helpful and it can be confusing, but because the solvent isn't actually participating in the reaction, it sometimes just doesn't get included on the arrow because it's not a reagent. It's not doing the reaction. So it does play a role. It gives us a liquid to move around in, but leaving it off or leaving it on is kind of the same thing, unfortunately. All right, last slide, last reaction for us to look at then. We're going to draw some products. Let me give us some boxes here. There's our boxes. So when we add our hydrogens in, we know we're going to add a hydrogen to each carbon. Because this is, let's see, let me start that sentence over. One of the things we have to pay attention to is stereochemistry, though. So this is a Syn addition. So I'm going to draw out just my carbon structure. Now, where the double bonded carbons were, that's where my hydrogens are going to add. If I add a hydrogen to each of those carbons, am I going to create chiral centers? Will I create stereocenters?
No.
Yeah, those aren't chiral centers. So if we aren't creating chiral centers, then we don't have to show stereochemistry, because if we put our hydrogen right here as a wedge and our hydrogen right here as a wedge, that's technically correct. They added in a Syn addition. They're both wedges. We could also do the same thing, showing them both as dashes. But neither one of those is a chiral center, so we don't need to include the stereochemistry in our answer. So it is a Syn addition, but we are not showing dashes and wedges because there's no chiral centers. So we went from our alkene to our alkane. All right, one more. Draw our carbon structure. So what about if we add a bromine to each of those carbons? Will we make a chiral center in this case? So if I add a bromine here and a bromine here, are either one of those a chiral center?
The left bromine?
Yeah, so the one on the right isn't, because there's two methyl groups added. Remember, our definition of a chiral center is that we have to have those 4 unique groups. So here's how we can show it to show our full answer. We're going to add one as a wedge, and we're going to add one as a dash. Sometimes, so the book likes to do this, the book likes to cheat. The book will show 1, and then it will just put plus En, meaning plus the enantiomer, just so you know what that means. But yeah, we would add the bromine in both directions, as a wedge and as a dash. And we would get a racemic mixture, so we'd get equal mixtures of both of those. Okay, questions at all about our last example here? Okay, I think we are at time. So on Monday, we will finish up this chapter. But in lab, we're going to talk about experiment number 8 today. So I'll hang out for a couple minutes, but go click on our Zoom link for lab, and I will see you guys in a couple minutes.
Thank you.
Thank you. What slide are we on? Number 7. Okay.
Professor Henry, I have a quick question.
Yeah.
So I emailed you a while ago the photo of my Beyond Labs because I got the loaner laptop. Can I re-forward you the email so I can get the points for that?
Oh, yeah. Let me see if let's see. So when I get emails of things I need to grade, I have a folder in my email that's just labeled to be graded. I wonder
Okay.
if
I didn't know if you preferred the email through Canvas or just regular.
it actually all goes to the same spot for me, so that part doesn't matter.
Okay.
Let's see, 2 grade. Yeah, I don't have one from you, so I wonder if I missed it or if it got lost somewhere. But yeah, go ahead and forward it to me again.
Okay, thank you.
You're welcome.
Bye.
I guess I can go unless Mario.
Yeah, Mario, did you have any questions for us? All right. I think that's it then, Emma. I will see you later.
Just a quick question. So I saw the